Hi everyone, welcome to the next video in the series. In this video we're going to be talking about limits at infinity. We'll do some reviewing of limits as they relate to vertical asymptotes and then also add horizontal asymptotes. So stay tuned. So here's an example where we have x approaches 2. This is not a horizontal asymptote, this is more of a vertical asymptote. You can see the graph here. You can see that at x equals 2, we would have a vertical asymptote, and then you can see the behavior on either side of it. But the first thing that you do when you're trying to evaluate a limit is you always plug in the value. And so when I do that, I end up with -1/0, which does not exist. Does not exist. Okay, so we look at the table of values and we see as x approaches 2 from the left, f of x is getting really, really small. And you can kind of see that over here. As x approaches 2 from the right, it also goes in the same direction. And as you'll recall, when we have a limit that is the same from both sides, then we could say even though the limit does not exist, the limit would go to negative infinity. Negative infinity. Okay? Okay, so basically there are two types of infinite limits. All right, and so there's a lot of writing here, but there's just two basic types. So you can see here there's a limit at infinity where it says as x approaches infinity and x approaches negative infinity of f of x, they're related to horizontal asymptotes. So what that says is as x approaches positive infinity, what is y doing? So you're looking at a horizontal asymptote. If it says x approaches a, like it did on the previous page, and it goes to infinity, then we're talking about vertical asymptotes. So this and this are important parts on this screen. So a limit statement that says as x approaches c goes to positive infinity means that it's going to increase without bound on either side. So in other words, something like this is going to act around a vertical asymptote at c, and then it's going to increase without bound on either side. Something that looks like this one, of course, is another vertical asymptote at c, and it's going to decrease without bound like the previous screen. So here's the rest of that statement. The horizontal asymptote is if as x approaches infinity, it goes to a number. So if it looks like if you had a horizontal asymptote here, right, you would say that as x approaches from this side, right, it approaches some value L, and as x approaches from this side, out this way, towards negative infinity, that it would approach the same thing. So that's a horizontal asymptote. All right, so here's an example. Let's talk about this a minute. So this goes to infinity on either side. So this is a limit that is looking for where is the horizontal asymptote. Because it's as x approaches infinity. Okay, so one technique, one way to do this, probably the easiest way to do this, is take the limit, analyze your function, and you can see that the function, the highest power of the variable is x squared. So divide every term in the whole function by the highest power. So divide everything by x squared. So I have 3x squared over x squared plus 2x over x squared. All right, and you can see that the x squared are going to cancel on that, and so you would have a 4 and a 3 down here, and then this would be 1 over infinity squared. Well, anything that looks like this is going to go to 0 eventually, right? Because your 1 over infinity squared is going to be infinitely small. And the same thing here, I would have 2 over infinity, which is also going to go to 0. So the limit as x approaches infinity of this function is 4/3. And so what that's saying is that there's a vertical asymptote, a horizontal asymptote at y equals 4/3. So as a limit goes to infinity, we end up having something called the big-little principle. And it says this: if you have 1 over a very large number, 1 over, let's say, positive infinity, 1, 2, 3, 4, 5. Think what happens. This fraction gets very, very small and will go to 0. Whereas on the other hand, if you have 1 over 1/10, 100, 1/3, 1/1000th, then remember that you take the reciprocal and multiply, and you end up with a very big number. And this is the principle that we're using when we evaluate limits that go to infinity. So here are two examples, and once again we are looking at the end behavior of a rational function. And we know it's a rational function because we have a polynomial in the numerator and a polynomial in the denominator, and we have that on both of these problems. Now you'll notice, and I didn't do a great job of writing the second one down, but the top has the highest highest exponent is x to the 4th. This one is just x to the 3rd. I reduced it. All right, so what we do when we have problems of this nature is that we want to determine what is happening at the horizontal asymptote. And so the technique for this is to find the largest exponent in the denominator. That's important, the denominator, not necessarily in the whole problem, but in the denominator. And then we want to divide every term by that number. So we would have x to the 4th over x to the 3rd minus 3x over x to the 3rd plus 1 over x to the 3rd, and then we would have in the bottom 3x to the 3rd over x to the 3rd plus 6x over x to the 3rd. And if we do a little bit of reducing in the top here, we have x, right, for this one. This, if we plug in the infinity, is going to go to 0, but this will be 3 minus 3 over x squared, and then plus 1 over x to the 3rd, and I'm having a hard time with 3's, and then 3 plus 6 over x squared. Okay? And I've done what I've told you not to do, which is put an equal sign when it's not equal. So I'm going to add the limit in here. All right, so as we do direct substitution, right, we're going to have infinity minus the big-little principle. So this is going to go to 0. This one will go to 0. This will go to 0. This will go to 0. So I have all of that over 3 plus 0, and so I end up with infinity. Well, if you end up with an infinity, this does not exist, and it would actually go to positive infinity. All right, it does not exist. So this one doesn't have a horizontal asymptote. If I had one like this over here, let me change colors to red, and we did the same thing. We would have the limit as x approaches infinity, and we would divide everything by x to the 3rd again. X to the 3rd and x to the 3rd. So I have 1, negative 3x, and I would have x to the 3rd. And then in the bottom, I would have this, 3x to the 3rd over x to the 3rd, and 6x over x to the 3rd, right? So this cancels, and becomes 1. And then everything that has 1 in the denominator, right, it would be 1 over infinity, so you have the big-little principle. So this is going to go to 0, this is going to go to 0, this is going to go to 0, big-little principle. And so I'm left with 1 over 3, and that would be the limit. Now, the interesting thing about all of this is that the rules for horizontal asymptotes say that if you have the same number, I don't know if you remember this, but the largest power in the top and the bottom, right, you compare them. If they're the same, like say this was 2x squared over x, then the horizontal asymptote would be y equals 2. If you have x over x squared, the horizontal asymptote would be y equals 0. And then if you had in the top, over the bottom, it would not have a horizontal asymptote. Now, it might have a slant asymptote, but it doesn't have a horizontal one. And so it's using this principle to find the limit. Okay, so one more situation that you will run into when you're doing limit problems of this type is I have over here written out the rule that you're going to divide by the highest power in the denominator. Well, what do you do if there's a square root? So we need to know one more thing before we can figure out what this power is. So if you look in the denominator and realize that the square root of x squared is plus or minus x, okay? And so remember, when you take the square root of something squared, there's always two roots. Well, you could write this a different way. You could say x, since that's the one of the highest power, would be negative or positive. Now, which one do you choose? Well, if the limit as x approaches infinity, you're going to use the positive one. And if you have x approaches negative infinity, you're going to use the negative one. So that's what we're going to do for this one. So I'm going to just write out here the limit as x approaches negative infinity, and we are going to divide all of this by x, because x, right, is the square root. So I'm going to have x over x, and in the denominator I'm going to have x squared plus 1 divided by the square root of x squared. But because this is negative infinity, it's going to be negative. All right? And this is the only one that will be negative. This x will not be negative. Okay? So, because we are using this over here, x gets replaced with x, but this down below would be negative square root of x squared. It's that root. All right, so the rest of this is just algebra. So I would have 1 over, let me do the limit, as x approaches negative infinity. And then if you'll write this, and then I'm going to move the negative to the 1 up here, get it out of the way. This will be x squared over x squared plus 1 over x squared. All right, now when you apply the limit, this will equal negative 1 over the square root of 1 plus 1 over infinity squared, which will, big little, right, which will go to 0. So this ends up being negative 1 over the square root of 1, which is 1, negative 1. So the limit as x approaches negative infinity. Now, what would it be if it approached positive infinity? Well, it looks very simply that it would just be 1. So it's this idea right here that you're going to use when you have the square root in the denominator. Now, if it's flipped over, if you had the square root of x squared plus 1 over x, right, let's say the limit as x approaches infinity, then the highest power is in the denominator, that would be x. So you would take the square root of x squared plus 1, and this would be in the top, over x over x. And because it's to infinity, this would be positive. And so you would do the same thing, only in the numerator. So I hope you took good notes on this one, because you will see this again in the problem set. The limits are kind of fun, and we're going to learn a rule later on called L'Hopital's rule, which actually makes use of derivatives, which is a lot easier, and uses the indeterminate, like 0 over 0, or like this. Okay? So take good notes. See you in class.